Okay, time to switch gears a little bit and focus on PV-specific requirements. We're going to move to the back of the book, Chapter 6, Special Equipment, Article 690, PV Systems. Let's talk about wiring methods. For that, we'll turn to Part 4 of Article 690, Section 690.31, Wiring Methods and Materials. And it specifically says in there, hey, all of the other wiring methods that are in the NEC, you're allowed to use them, provided that they are suitable for the current and voltage and the conditions and the exposure, and we'll get into some of those details in various places throughout the course, but those aren't off limits to us. We do, however, have some other wiring systems that we can use, listed for PV system use, or part of a system that they're listed as part of, like the wiring that comes with microinverters, for instance. We can use that stuff too, in addition to general wiring methods and materials in the front of the National Electrical Code. So that's where we would go to Chapter 3 for additional details. We'd be looking at things like general requirements in Article 300, conductors for general wiring in Article 310. We'll be turning to both of these when we do things like conductor sizing. And in Chapter 3, we can also turn to the individual articles for specific cable and conduit types, requirements for PVC wire, or specific kinds of cords or cables that we may be using. Those will also have their own article in Chapter 3 as well. So, speaking of Chapter 3, Article 310, conductors for general wiring, a good one to know about is Table 310.4a. This gives us conductor applications and insulations for those rated up to 600 volts or for other ones that are marked up to 1,000 volts as well. So it covers both of those. And it tells us what conductors are suitable for what applications and installation conditions. What is their insulation rated for? Is it sunlight resistant? Is it moisture resistant? Can it be used in oily environments? Whatever those may be, that's where we'll find those kind of details. 690.31c further specifies that requirements for PV array wiring. It says, hey, inside the PV array, so within its boundary, for the DC circuits, we have to use USE2/RHW2 that's also marked sunlight resistant. That would be a wire. It's dual rated USE2 RHW2 sunlight resistant. Or we can use a specific solar wire called PV wire, or we can use DG cable, a multi-conductor jacketed cable, distributed generation cable that's also targeted towards PV applications. Okay, so those are required within the PV array for DC circuits. So that whole thing I just said about you can use all the other wiring systems in the code, not here you can't. We have specific requirements for this part of our PV array wiring. Now, of course, these conductors have to have the right voltage rating. We got to use the right connectors and crimping tools. And we can only run our single conductor cable within that PV array boundary. Important to keep that in mind. There's not a lot of wiring out there that's not, running from one pole to the next from the utility lines where we use single conductor cable in free air. There's some of it, but it's not that common. Usually we have multi-conductor cables that have an extra jacket around them and they're in a wall, or we have single conductor cables that are in conduit or some other kind of protection. So this is important to understand. We can't just run this wire from the array, lay it on the roof, and then come off the roof and it's just dangling in the air down to our inverter. It's within the array. Once we're outside of the array, well, now we've got options. In fact, all of the options that are in the code, and we'll look at some of those later on. 690.31a, wiring systems, specifically says if PVDC circuits are greater than 30 volts and are readily accessible, they have to be guarded. That could be by height. They have to be in a raceway, or they have to be type MC, which is metal clad cable. Not the MC connector you may be thinking of that are the plugs on the modules. Metal clad cable. It's a armored metal jacketed cable with multi-conductors inside of it. Okay, what's readily accessible? Well, anytime you have a question like that, and this looks like a term that was probably defined, we'll turn to Article 100. We'll look up accessible, readily, and that'll say, hey, something's readily accessible if you don't need a ladder to get at it or a tool to get at it, basically. So this is a good example here. We're looking at a ground-mounted system, and you can see this isn't that high off the ground. I don't need a ladder to get at these. But with this lattice behind it here, I need a tool to get at it. So I've guarded this by putting the lattice there, and it's in a readily accessible location, but it's not readily accessible because I'd need to get out some tools to open that up and get at that wire. I always like to think of it as, hey, this is like the jungle gym. If I'm 5 years old, I'm climbing all over this thing if I can get at it, and I don't want somebody grabbing one of those single conductor cables and dangling on it and pulling it out, and now there's a shock hazard or a fire hazard or whatever it may be. So 30 volts or greater in readily accessible locations. So that means not on a roof. Like a roof is not going to be readily accessible. Maybe in some instances, if we have a commercial building where there's a dedicated stairwell where I can get up to the roof access very easily, that could be considered readily accessible potentially. But a roof of a house, no, not really. You need a ladder to get up there in most cases. So it wouldn't apply there. We're really talking about pole mounts and ground mounts. And so what are some of the options? Fences. Fence it off. Lock it up. Can't get at it easily without the key, or climbing the fence. That's above and beyond. We did what we could there. We rendered it non-readily accessible. Lattice, like we show here, or the other option would be height. Something we might do on pole mounts. Make it high enough so it's at least, the wiring is at least 8.5 feet above grade. That is considered to be guarded by height. You can turn to 110.27a4 for more details on that. So something we want to keep in mind, may not matter depending on where you're installing your array, but anytime we've got a DC circuit over 30 volts, we've got to take this into consideration. Identification and grouping requirements for our PV system wiring is in section 690.31b, and it says, hey, we can put stuff together in the same enclosure, in the same cable, in the same raceway. We can put some things together, but not other things. And it really comes down to what can I put with PV system DC circuits and what can I not. So if I have a PV system DC circuit running down from the roof, let's say, in a conduit, I can put other circuits, other conductors in there, such as class 1 remote control signaling wires or power limited circuits. These could be something like a circuit that controls a rapid shutdown system for a roof-mounted PV array. I can put those together. It's part of the PV system. It's not the current carrying DC conductors, but it's part of that PV system. What I cannot put in there are non-PV system circuits or the inverter output circuit. So even though that inverter output circuit is part of the PV system, I cannot mix that AC circuit with my PV system DC circuits. There is a caveat. If there's a barrier or a partition. So this is kind of a good example here because this is one that's changed over the years. This is a system in our lab yard in Paonia, Colorado, and we've updated it to comply because these rules have kind of changed over the years. It used to be we could put them together, then we couldn't, and then we weren't sure, and now it's pretty clear we can't. So let's look at what's going on. We've got DC coming down off the roof, comes to a DC disconnect, into the inverter AC output. They're separated. This system used to run a little different. We had it set up so that we came down into this gutter or trough and then up into the disco, back out of the disco, up into the inverter. So we had AC and DC together in here. That became a no-no. It was okay. Now it's not anymore under the 2020 NEC. Unless we had gone and done something like put a partition in there. You can buy partitions to separate the sides of this gutter, or we can buy partitions that'll separate top from bottom. There's other ways to deal with that. But in general, AC and DC, the AC from the inverter, the DC from the PV array cannot mix inside of an enclosure cable or a raceway unless you're putting partitions or barriers in there. Now, there are some exceptions. PV system DC circuits of multi-conductor jacketed cable, metal clad assemblies, or listed wiring harnesses identified for the application. What does that sound like? That kind of sounds like something special that goes along with a microinverter system or a DC to DC converter system. It's specifically listed to be used this way. It's been tested. It's okay. And that's fine. Now, we do also have to make sure that when we do mix conductors together, that whatever the highest voltage of any circuit is inside of there, that all of the other circuits, even if their voltage that they have to deal with is less, is at least as high as the greatest one. So if I have 600 volt DC and then I've got like a a 50-volt signaling conductor or whatever it may be to some kind of system or monitoring or whatever, that lower voltage circuit is still going to have insulation rated to 600 volts of the DC circuit that it's in there with. So important to keep that in mind. 690.31b1 goes a little bit further and talks about identification of these circuits. So grouping and now identifying. We group them together. Well, let's identify what's what here. So PV system DC circuit conductors have to be identified at all termination, connection, and splice points. So we've got identification here, right? We're terminating these, and there is our identification that goes along with it. This is telling me combiner box and string numbers, for instance. And then on the output here, I've got my PV output circuit of this combiner box. It's telling me what combiner box number this is, and it's running onto an inverter, whatever it may be. So this identification is accomplished by color coding, marking tape, tagging, or here it is, other approved means. What is your AHJ going to allow you to do? Now, I want these to be durable and suitable for the environment. These aren't just stickers. These are heat shrink. They're not going anywhere. Stickers tend to not last that long. So hopefully your AHJ wouldn't approve it if you use stickers. Or if you are using some kind of marking tape, it's rated for that particular type of environment, realizing that outdoors is a lot more harsh. Even if it's a combiner box inside an enclosure outdoors, it's a more harsh environment than something inside a building in conditioned space. Now, if we're not using color coding for polarity identification, we need to use some kind of approved permanent marking. All right, if the wires are color coded, they're going to stay that way. Now, sometimes red fades to white in the sun, but inside the enclosure, you should be able to tell it's not going to fade. Otherwise, if the wires aren't giving it the polarity identification, positive and negative, say all the negatives are black, all the positives are red, we need to use some other type of approved permanent marking. As I said, labeling, sleeving, shrink tubing, something that's not going to fade or fall off or fail in that environment that the conductors are exposed to. So talking more about identification, and when you think about it, on the DC side of the system, what's really important? It's polarity. It's really good to know things like which string this wire comes from and which combiner box we're in. That's really helpful for installation and service. But as far as not damaging stuff or creating accidental short circuits, polarity, what's positive and what's negative, is really kind of the most fundamental important thing. So we have to mark polarity on the conductor insulation. Now, we could be doing this via color coding, right? It could be all the red wires are positive, all the black wires are negative. That's one way of doing it. If they're not color-coded like that, then we need to mark them with the polarity either by using plus signs or the word positive or POS, whatever it is. And the conductor we're marking for our positive conductors cannot be green, white, or gray. Can't do it. Cannot be green, white, or gray for our positive conductors. Any other color's fine as long as they're marked with plus or positive or POS. Negative conductors, we're talking non-solidly grounded systems here. I don't want to go down that rabbit hole right now. This is most PV systems these days. We'll talk about that later elsewhere in the course. But our negative conductors, the negative symbol, negative or neg, whatever it is, the conductor cannot be, however we choose to mark it out of those three options, it cannot be green, white, gray, or red. So red we're reserving for positive. Positive doesn't have to be red. Negative cannot be red. Kind of the convention is positive red, negative black. But you can use any color you want. You can use any color you want except for the one shown here. Why not green? Well, come on, green's grounding, right? Why not white or gray? White or gray is a solidly grounded conductor. Neutral on our AC system. So we don't want to use that for one of these conductors. And then we have the caveat, just to kind of go along with the convention that's existed for quite a long time, red positive, black negative. Black doesn't have to be negative, just can't be red, white, or gray, or green. Positive doesn't have to be red, it just can't be green, white, or gray. And then you can take it from there. Now, there is an exception. If my conductors are arranged by how they're spaced out or how they enter an enclosure that things are obvious, I don't need further identification. In some cases, it's pretty obvious. Like it's coming in from one end, it's going to the inverter, pretty clear what's going on here. But not always. And It may be obvious to you, it may not be obvious to the AHJ or inspector. So anytime we have this kind of subjective sounding allowance, I always want to clear it with them before moving forward. So as I said, we didn't want to go down the rabbit hole of non-solidly grounded and solidly grounded, but I do want to put it out there now, and we'll be touching on this later, that these days there are very few, especially the types of systems we're talking about here, solidly grounded DC PV systems. So you really don't want to be using white or gray. You shouldn't be using white or gray. What did I just say here? White or gray is a no-go for either positive or negative. You may see white or gray on older systems. It used to be appropriate based on how we classified and talked about our systems, but not anymore. So we should not be seeing white or gray anywhere except on where? Well, the AC side. It could be our neutral conductor, white or gray, on the AC side of a system. DC side, can't do it. So don't be buying it. Get rid of it if you have it. Use it up fast and start following these conventions. Continuing on, identification and grouping. If conductors from more than one PV system share the same junction box or raceway that has a removable cover, then we have to group those separate system conductors together. We need to do it at least once and every 6 feet thereafter. There's an exception, again, if it's obvious what's going on here, we don't have to necessarily group them together. So it really depends on the layout of stuff. This is an older system here. This is an older system, but I like it, it's kind of like it as an example, and part of me doesn't, because what do I see? Well, these are DC conductors, and I see white. So that's telling me this is older. Now, it wasn't a code violation when it was put in. In general, those white wires are going to be the negative wires. It's not good anymore. We can't do that. But I like this as an example because we've got two inverters here sharing this gutter. We've got DC coming in. We've got our AC conductors here. And to me, it's pretty obvious what's what. Pretty obvious what's what. Here's DC to this inverter. Here's DC to that inverter. They come in, they go over. It's pretty clear what's going where. Right? This is coming out. You can't really see it as well there, but that's out of that inverter. There's our AC. Coming out of this one, there's our AC. Now, maybe over here, where these AC circuits run together into that conduit, maybe there for sure it's harder if they're all together and loose. I don't know which ones are which. Maybe they need to be bundled there. So again, it's a little bit subjective when we say, hey, it's obvious what the grouping is. Again, maybe to you, maybe not to somebody else. That somebody else's opinion may be the one that matters. So see how they feel about this grouping requirements. It's nothing very tedious, really. It's zip ties. It's often helpful for performing service down the road to have these things grouped together. So it's really a good practice to follow either way. Okay, up next in part 7, we will dive into some more, that's right, more 69031 requirements. Let's finish it up there soon.